So let me start off by talking about some of the joints in the bionic hand. So the vast majority of the joints that you'll see are just simple hinge joints, and that includes all of the joints in the thumb, most of the joints in the finger, and a few others here and there. So the way that these work is they have a simple pivot, which in this case is just a bolt. Now having a bolt as a pivot is obviously in no way ideal. The bolts are just kind of there as a placeholder. Obviously in a final thing I would have the bolt only threaded at the very end, so that it would have a nice long shaft to rotate around. But as a sort of proof of concept piece, they are just the pivots are across just these threaded bolts. Now the way that they're actuated is by using a sort of cable and spring arrangement. So all the motors are mounted in the forearm, and those motors have little pulleys on them which pull some cable through a cable sheath. If you think of like a brake cable in a bike, you pull the brake, which pulls a little bit of wire through the cable sheath, which actuates the brake calipers at another part of the bike. That's the same kind of idea here, except instead of a manual brake lever that you pull with your hand, it's a motor pulling the wire with a pulley. So when the motor pulls the cable through the sheath, that contracts the finger by using the inner cable to pull the finger joint downwards, and then when the motor relaxes, a little torsional spring in the centre of the joint, wrapped around the pivot point, returns the finger back to a neutral position and maintains tension on the wire at all times. So you'll see there's a little animation of this working. Hopefully that sort of clarifies it if that explanation wasn't satisfactory. Now this sort of cable arrangement is something that's used quite often in animatronics because it's quite easy and simple to actuate something and make it do some quite complex motion without having to have any actuators in the joint or near it even. It can be as far away as you like. But obviously there are some inherent problems with this. So the further the distance you put between your actuator and the thing that you're moving, there's a lot of wiggle room between all the sort of components in that chain, and so eventually it is inevitable that components will sort of come out of calibration. So eventually the fingers will be they'll not be in quite the same positions as they were to start with, and because the inner cable has room to move in the inner sheath, as the fingers move around and the outer cable is moved around, there's the potential for the fingers to move slightly, just as the tension of the inner cable is just like moved slightly. If you had an inner cable that was the exact same diameter as the inner diameter of the outer cable, if that made any sense at all, then you wouldn't have to worry about it, but you would obviously have to worry about friction. So for something where you're trying to just get a really lifelike motion and you're not too concerned about the accuracy, then it's not too much of a problem. The solution would be to have a feedback sensor in the joint itself, like a feedback sensor in every single joint, and then it could be more or less perfectly accurate every time. But obviously that would add a lot of complexity to the assembly. It is something that could be done, it wouldn't be too much trouble. But using the kind of really small potentiometers that are used in the control glove, there's no reason why you couldn't have something like that. And maybe in a future redesign that will be something to think about. If this was used as a real prosthetic hand, you would need something like that, absolutely, because you couldn't be recalibrating it all the time, it just wouldn't be practical. So having a feedback potentiometer at every single joint would probably make the design a lot more reliable. But regardless, there'd still be some problems with the pulley mechanism, and most of them you could make a lot better just by using tighter tolerances between the inner cable and outer sheath, things like a better pulley and a better securing mechanism on both the pulley and the point that you're actuating. There's a million little tweaks that you could make that would make this a lot better, but in the demonstrations it did seem to work sort of okay as a proof of concept, you know. So one quick other point I want to make about the hinge assembly. Looking at the exploded view, you can see there's like an unbelievable amount of components in this hinge, when really there only needs to be the two parts that are moving relative to each other and the pivot point, which is the bolt that's going through the centre. There isn't really too much need for any other components than that. It's just because I had this really weird idea of how strong 3D printed parts were, based on the sort of bad experiences that I'd had with my cheap printer, which is now running a lot better because of some upgrades I've made. It's also just because I wanted it to be as strong as it possibly could be, and I didn't really realise that PLA can actually be really strong. But when I was designing it, I made it so that very few parts that I printed would have any sort of holes running through any side faces, and the vast majority of the holes would just be up through the Z-axis of the 3D printer. And I also tried to print everything in really simple shapes, no overhangs, you know, just as simple basic shapes as possible, so my 3D printer would be able to print them quickly and strong. But I think I was seriously overcompensating for the limitations of 3D printing, because I've ended up with this design that has way too many parts and way too many fasteners. And the other thing was that because I had to do so much 3D printing during this project, my 3D printing skills actually increased massively, to the point where I'm much more confident printing odd shaped parts now. And really, even on my cheap printer, there's nothing wrong with doing that sort of thing, and it can be made really strong. But honestly, it probably makes it look a bit cooler than it really is in the renders, having all these bolts. But I think in a future redesign, I definitely want to redesign it to have like as few fasteners as possible. Like, I was thinking even the shell components could be like snap fit. Become a lot more confident with designing two different 3D printed parts to fit together, and the sort of tolerances you need between them to be able to achieve that. This also leads into another really big problem with the design, and that's that I've limited myself almost entirely to 3D printed parts. I'm going to talk about that in more detail a bit later on. So, going down to the knuckles of the fingers, these are MCP joints. I believe they're called metacarpophalangeal joints. In a real hand, these are condyloid joints, which is like it's like a weird ball socket joint, but rather than being a ball, it's kind of like a sort of ovoid shape. So when the finger moves, it's got obviously the two axes of motion are quite easy to see. You can see it can go up and down, or it can go left and right. But you'll also notice that the finger turns inwards slightly. It sort of points inwards towards its axes of rotation when it's moving left to right. And this is something that I thought would be quite important for certain grip types. Things like if you wanted to pick up a ball, and you splay your fingers to go and pick up, you know, like a large ball, you'll see that your little finger and your index finger sort of curl inwards, and I thought that would be quite an important sort of grip configuration to be able to pick up something like a ball. So I thought for a really long time about how I could make a mechanism to, without really overcomplicating it and adding too many actuators, sort of automatically have the finger twist inwards as it did the lateral side-to-side motion in the MCP joint. So I drafted a few ideas, and I decided that it'd be best just to simplify it to two axes, like a double hinge joint. Although it still sort of bothers me that I didn't manage to find a solution to that, and I feel more confident now that if I went back I could think of a better way to do it. I'm fairly certain it would be possible. I thought of some ideas of how you could do it with some sort of linkage assembly, but I couldn't think of a way to make it strong enough, and definitely not with 3D printed parts. It just wouldn't be strong enough. But that's actually where I started designing the assembly, because I was really keen on having that little twist inwards, and that's the point that I started building the hand from, just because I was so insistent on getting that range of motion, but I couldn't figure it out. I made some assemblies and had some ideas, and I got something that sort of worked okay when I simulated in SolidWorks, but it wouldn't really have been strong enough to have any real force going through it, so I ended up just simplifying it to this double hinge joint. So there's nothing really special about this design. There's a joint in the centre that allows it to move left to right, and a joint that allows it to curl. It should be noted though that the lateral movement, rather than using a torsional spring like all the other joints, it has cable from both ends of the pulley, so rather than use a spring to return it back to a neutral position, it sort of pulls from both sides. So that's useful because I wouldn't know which side would necessarily need to be exerting more force, so, you know, the left and right movement should move with an equal amount of force. So most of the joints in the thumb work exactly the same as the hinge joints that I talked about earlier, except just a little bit larger, apart from the base of the thumb. Now, the base of the thumb is a saddle joint. It's the only one of its kind in the human body, although when I was looking through the literature, it seems like a lot of people disagree about how to classify what this joint is at the base of the thumb. But it's a really complex joint, and it's a kind of it's like a concave surface interacting with a convex surface, and it allows the thumb to move through some quite complex ranges of motion. So if you look at your thumb, you'll see there's two segments of the thumb that are sort of protruding from the palm, and then there's another bone that's sort of built into the palm, and it's surrounded by muscle. As I did mention this a little bit in the previous video when I was talking about the control glove. All that muscle around the bottom bone of the thumb makes it quite difficult to measure how it moves. But I believe there's something ridiculous like 8 muscles or something in the thumb. There's ones that connect to like the carpal bones in the base of the hand, and then I believe the metacarpal bones of the index finger on both sides by the looks of it. Basically, it was way too sort of complicated to try and directly emulate. I couldn't just have a cable for each one of the muscles, because I think that'd just be ridiculous and I'd have way too many actuators. So I tried to approximate the movement of the thumb as best I could at that joint, and I ended up having 2 axes of motion. I could have put another on, but when I did the grip type testing for the hand, I found that it was more or less all I needed. So yeah, so having 1 axis of motion being the sort of swing around the fingers from all the way from opposing most of the fingers to swinging back and sort of being facing the same direction as the fingers, and this uses a little assembly with 2 little bearings that allows it to swing round, deep groove bearings, so they can have a little bit of force through their axes of rotation, and then a little sort of spring piston assembly to bring the thumb in towards the fingers. So that piston is a little bit jammy, really. I'm not too pleased with it. It's the kind of thing that really just probably shouldn't be 3D printed. I could make it on a lathe or just buy something that'd do that task, but it does kind of work, at least it's a proof of concept, but it also presents some problems about the management of the cables through it. So probably more development, more focus is needed at the base of the thumb to try and emulate that joint better, because it is just so complex, but it's also so critical. It's just so important to have the thumb working properly. You know, without the opposing thumb, we wouldn't be able to do anything with the hand, really. And then at the same time, you're also limited by how much you can measure it with the control glove. So the base of the thumb is definitely a challenge and something that still needs work. So here's another sort of weird range of motion that I wanted it to have. The metacarpal bones are slightly flexible, and you'll notice that if you just sort of play around with your palm, you'll notice that you can move your little and ring finger metacarpal bones by sort of squeezing the muscles below your little finger in your palm. So this was another thing that I thought would be important. I wasn't able to find much research into that specific sort of degree of freedom, but I feel like it is quite important, even though it's something that you don't really pick up on. Whenever you go and grasp something, your knuckles sort of move downward, and depending on what you're picking up, I feel like that might be quite an important range of motion. But that is something that I'm sort of a little bit unclear of. It just seemed to be like quite a poorly researched and poorly understood thing to happen, and it might just be something that's sort of locked to other movements. It might not be something that you can really control individually, but I wanted to put it in anyway because I guess my intention was to just cram as much degrees of freedom and degrees of actuation as possible, and just try and cram everything in there so it could be as organic looking and moving as possible. So this is the one thing that just didn't really work, because I'd used a little bit of sort of inner tube going across the knuckles to try and be the elastic thing that would return it back to a neutral position. Yeah, the inner tube wasn't really good enough for bringing it back, and it just kind of like made it more difficult to actuate. Something that more directly opposes being bent, like a little strip of spring steel or something like that, would have been a lot better in place of that inner tube. This is something that I'm just not sure if it's necessary at all. I don't know if it adds anything really to the hand. It's something that I'd be tempted to just completely take away, because it adds so much instability to the structure of the hand, and there's kind of like no benefit to it being there. It was kind of just because as I've said at the beginning, the idea is just to design a hand that's as close to a real hand as possible, with kind of like no regard really for how easy it would be to control. Like the pitch was just in the future, when there's no restrictions on how we can control bionic hands, like myoelectric technology, detecting nerve impulses in the residual limb. Like, say we could just detect everything in like super fine detail, what kind of amazingly complex hands would we use rather than the limited ones that we have now? But yeah, that's something that I could probably just get rid of, honestly. I have seen bionic hand designs that kind of integrate like one or two hinges sort of in the palm to sort of it sort of combines the motion of moving the metacarpal bone with the sort of inwards twisting that I was describing earlier, and it does allow the little finger to sort of oppose the thumb more directly. It's something that I need to sort of research in more detail. Maybe I was in too much of a rush to sort of start designing, and I sort of neglected certain joints, even though I did produce a wealth of research, and my thesis was marked very highly, in fact. But the hand is such an enormously complicated biological mechanism that there's just so much you could look into, and trying to emulate every single joint is something it's just a really complicated process. So then there's the wrist. The wrist was kind of challenging because I wanted to make it as small as possible. The wrist in our hands, I'm just talking about the flexion and the left to right. I'm not talking about turning your palm over as of yet. But that motion in our hand is just controlled by muscles in the forearm, just like the fingers. I didn't really have any more space in the forearm because all of the forearm was taken up with the actuators for the fingers. So I ended up sort of integrating servo motors into the wrist right where it bends, and then using like timing belts and pulleys to try and get a little bit more torque out of the motors, and obviously transfer the force across. I did have a little bit of trouble fitting these quite bulky motors into a small enough space, and ideally I'd like the wrist to be a little bit more streamlined, but it did seem to work okay, even if it was maybe the motors weren't quite as strong as they needed to be. But that's also a problem with the weight of the hand, which is a problem with the design sort of overcompensating for the limitations of or my idea of the limitations of 3D printing. So people are asking me how can it be fixed and how can you get it working, but realistically the problem's sort of deep rooted, and it needs to just be started from scratch to be able to have it working perfectly, because it is just too heavy and there's like 1,000 little tweaks that need to be made. It's just like one step in a iterative design and prototyping process. But yeah, the wrist doesn't work too bad. Now the turning over of the palm, this is something I thought about for a while, because in a real hand you have two bones, a radius and an ulnar bone. Your ulnar bone forms most of the elbow joint, while the radius bone forms most of the wrist joint. So when you turn your palm over, the radius bone moves across the ulnar bone, which stays stationary. So effectively you turn your palm over while your elbow stays stationary. This is something that I just didn't have time to figure out. I was looking at this great big massive fuck off stepper motor and trying to imagine how I could get it to turn the entire thing over, but in the end I just didn't have time to figure it out. I mean, obviously you could just have one motor just sort of twisting the entire arm through the centre, and that's what I was thinking of doing, but in the end I just wasn't happy with anything other than the sort of radius turning over the ulnar assembly, because it wouldn't be biomimetic, and I wouldn't have been happy with it. But that's something that in the future I'd like to figure out. So thanks for watching. There's going to be another part on this because there's still a lot more to cover on the bionic hand. But there's also a video out about the control glove, which was another important part of the project, so check that out if you're interested, and I'll see you in the next video.